Hi, welcome back. Today we're going to continue on with our exploration of Ginzburg-Landau theory, deriving a set of equations of motion and trying to learn some things about superconductivity from it. We're going to use quite a few results that we used either in the previous lecture on Ginzburg-Landau theory or on earlier lectures where we studied London theory of superconductivity. We're going to piece together lots of different pieces, and I will quote some of the results that we derived earlier. If you don't remember how these things were derived, look back either to earlier lectures or in the notes. I'll try to remind you a little bit where some of them come from. So where we left off, we had the Ginzburg-Landau free energy, which is a functional of psi. It's integral over space, 1 over 2m star, I guess minus the kinetic term, minus IH bar gradient, minus E star A, the vector potential applied to psi squared. And then there's plus the potential, what's usually called the potential, alpha 2 psi squared plus alpha 4 psi 4, psi to the fourth power. And then there's also the electromagnetic term, integral dr of b squared over 2 mu plus e squared over 2 epsilon naught. Okay. Now, what we're going to do now is we're going to derive a set of, I even wrote this down, equations of motion in Ginzburg-Landau theory. And the way to do that is to, as usual, you functionally differentiate the free energy and set it to 0. That extremizes the free energy. And this derives a nonlinear Schrodinger equation, nonlinear Schrodinger, just like we did for the Gross-Pedievsky equation for the neutral superfluid, but now the difference is that we are minimally coupled to a vector potential. So we get minus I h bar gradient minus E star A squared with psi. So the kinetic term now is coupled to the vector potential plus alpha 2 psi plus alpha 4, I guess plus 2 alpha 4 psi squared psi equals 0. Okay, so this is our new nonlinear Schrodinger equation, now exactly like the Gross-Pedievsky equation, except now minimally coupled to vector potential. In addition, we can take the functional derivative with respect to the vector potential and set that equal to 0 as well. And this is a nice exercise in functional differentiation. If you do it, one just has to be a little bit careful to keep track of the indices appropriately. What you end up getting is minus E naught dE dt plus curl of B over mu naught equals E star over 2m star, then psi, I guess P minus E star A psi minus P plus E star A psi star times psi. And okay, so this is great here, because this expression here is what we previously called the superfluid current. When we talked about London theory, we postulated an order parameter psi, and we said that if psi is like a wave function, the superfluid current should look like the current operator coupled to a electromagnetic vector potential. So it should have this form. This is the form we postulated when we said that there was a superfluid current several lectures ago. And on the left-hand side over here, just from Maxwell's equations, this is, in fact, just the current. So this now justifies our prior conjecture that this should be the form of the superfluid current if you have an order parameter which we call psi. Now you can do exactly what we did previously. We can set psi to be uniform, set the order parameter to be uniform, and we recover the simple form of both London equations in London gauge. That J, the total current, or J superfluid, is going to be E star squared over M star psi squared times the vector potential, and identifying psi squared as the superfluid density, we can write it in this form, which is the form we wrote before. The only thing that we can add now that we've been studying Ginzburg-Landau theory is that psi squared, the uniform value of the order parameter, is given by alpha 2 over 2 alpha 4, and this is what we identified as superfluid density. Now, where did this? Just to remind you, so I found that the equilibrium value of the superfluid, the magnitude of the superfluid order parameter psi, is alpha 2 over 2 alpha 4, and that comes from, scrolling back up, just differentiating this potential here and finding the minimum. And the minimum is, if alpha 2 is positive, the minimum is at psi equals 0. That means you're above TC. And if alpha 2 is negative, you get a non-zero value of the superfluid order parameter. Okay, so we've sort of recovered London theory. We can recall we took some of these London theory results and we put them into Maxwell's equations, and we derived a screening length, or London penetration length, London penetration depth, depth or London length, and that we wrote previously as square root of m star over E star squared ns star mu naught, square root of that whole quantity. We can, if we want, we can rewrite that in terms of these Ginzburg-Landau parameters, alpha 2 and 2 alpha 4, which I guess we'll do now. So it's 2 alpha 4 m star over E star squared, absolute value of alpha 2, and mu naught downstairs. Okay, so this, again, this London penetration depth is the length scale over which magnetic fields are screened in the Meissner effect. The magnetic fields are expelled from the superconductor, and they're expelled due to screening currents that live up to a London penetration depth from the surface. In addition, there was another length scale we derived in the previous lecture when we talked about neutral superfluids, but it's exactly the same for charged superfluids. There is what you call the coherence length. Which is the draw that a little bit better. Coherence. True story that when I was in 7th grade, my English teacher said that my handwriting was unacceptable, and he made me stay after school for an entire month every single day to work on making my handwriting better. And I was so bitter. My handwriting still isn't very good, but I'm actually very grateful to him that he did that. And the true fact, despite the fact he was an English teacher, not a math teacher, his name was Mr. Fraction. So, whatever it's worth, I believe he's passed away since. I'm thankful to Mr. Fraction. Okay. But boy, was I mad at that time. Okay, so the coherence length, which hopefully now you can read, I wrote coherence length here, is the length scale over which the superfluid order parameter can be changed, in which its phase can be changed, or which its magnitude can be changed. It wants to stay constant, but since there's a gradient term in the free energy, it costs you energy to change the value of the superfluid order parameter. If you force the superfluid order parameter to change its value, either by twisting its phase or by giving it a boundary condition, it heals over the length scale of the coherence length. and we calculated that coherence length is h bar squared over 2m star alpha 2. Now you'll notice that both the London length and the coherence length are inversely proportional to the square root of alpha 2. And you recall that alpha 2 was this parameter which is proportional to the distance to the critical temperature. So alpha 2 changes sign as you go through the critical temperature. So both lambda and psi are proportional, well, they're both proportional to 1 over square root of absolute alpha 2, or proportional to T minus Tc to the minus 1/2 near Tc. Okay? So that's both of them are diverging near the critical temperature. Now, we're going to actually need one more fact about the London length and the coherence length, which is that what the product of the two are. I'll write it out now, and maybe I'll make this a little smaller so you can see what I'm doing while I do it. So let's just write out this product. Lambda chi is the product of these things, so it will be 1 over absolute alpha 2. Then there'll be an h bar over e star, and we're left with a square root of alpha 4 over mu naught, and I think m star cancels. There's no dependence on the mass. We're going to use this later on, so that's why I wrote it here. Another thing to notice is that h bar over e star here, this quantity that I'm putting in parentheses, h bar over e star is actually the superconducting flux quantum divided by 2 pi. That might also be useful as we go along. Now, another thing that we derived in a previous lecture, several lectures back, was the condensation energy from thermodynamics. Condensation energy, which is the amount of energy that you gain by letting the system become superconducting instead of forcing it to be normal. In other words, how much lower in energy is a superconducting state than the normal state at zero temperature. And we derived that the condensation energy, E condensation per volume, is actually related to the critical field in a very simple way. Now, what we can do is we can actually rederive the condensation energy per unit volume from Ginzburg-Landau theory, and that will help us figure out what these Ginzburg-Landau parameters are. So how do we do that? Well, recall that above Tc, the Ginzburg-Landau free energy functional looks kind of like this. It's quadratic, so this was free energy as a function of psi, so this is T greater than Tc. And then for T below Tc, it looks like this. Right, so this is free energy psi, and this energy here is the condensation energy, E condensation. It's how much lower in energy is the ground state when you allow it to become superconducting. When you go to the minimum of the free energy, this is at called psi naught here, the energy is now below zero. Above Tc, the free energy is 0 here. When we get down below 0, the amount of energy we've saved by becoming superconducting is the condensation energy. So F normal is 0 in Ginzburg-Landau theory, and F super is, well, it's alpha 2 psi naught squared plus alpha 4 psi naught to the fourth, and recall that psi naught is at the minimum square root of alpha 2 over 2 alpha 4, and we just plug that in. And if we plug that in, we discover that F super, the free energy, is or the condensation energy, is just minus alpha 2 squared over 4 alpha 4 for alpha 2 less than 0. Okay, so comparing this expression for the condensation energy in this expression for the condensation energy in Ginzburg-Landau theory with this expression for the condensation energy, which we derived basically from London theory and thermodynamics, I'd set these two things equal to each other. I guess this is per volume and per volume, since we were looking at this quantity. This is free energy density, these f's, so I should probably make these small f's because these are free energy densities. Integrate them over all space to get the total free energy. So we set the condensation energy in Ginzburg-Landau theory per unit volume to the condensation energy here per unit volume, and we come up with the identity that alpha 2 squared over 4 alpha 4 is mu naught h critical squared over 2. Okay, a rather beautiful formula. Oops, I want that to be a square. Nope, still not giving me a square. There, well, okay, it's vaguely a square. Okay, good. So, so that means just turning this equation around, we can write h critical is absolute alpha 2, 1 over 2 mu naught alpha 4, which immediately tells us one thing that's quite useful, that the critical the critical magnetic field is proportional to alpha 2 here, right, okay. I think I might have said by mistake that this equation that we derived up here is only. I think I said something about being zero temperature, and this equation is not restricted to zero temperatures. It's general. It holds at any temperature, because any temperature below Tc. So here, what we're going to do is we're going to plot something I plotted before, the phase diagram for a superconductor. That there's something like this. This is H on this axis. This is normal. This is super. This may be a type 1 or a type 2 superconductor. This line here is Hc of T. Hc of T is this line. And what this tells me here, the fact that Hc is proportional to alpha 2, is that this line here is linear. Use Tc linearly. Sorry. So this axis is T. The axis is T, and this point is T critical. And as you leave T critical, as I drew in red here, it leaves the axis linearly, because alpha 2 is linear as you go away from Tc. Okay, so this tells us immediately that the behavior of the phase transition line as we get close to Tc is a function of magnetic field. Okay, so that's a sort of important piece of information. This statement is true in Ginzburg-Landau theory. It may not be exactly true in when you go beyond Ginzburg-Landau theory. Okay, so I want you to be a little careful about that. Now we're going to then manipulate this equation just a little bit more. This expression for the critical field, and we're going to use this equation back up here for the product of lambda and psi. So let me just cut this equation here. Okay, maybe I'll cut the whole thing here. Copy this so we can use it, and move it down here. Paste. Okay, there we go. All right, and then we are going to, well, we'll notice in this equation here we have an alpha 2 and we have a square root. We have an alpha 2 and we have a square root of alpha 4, exactly like we have here, an alpha 2 and a square root of alpha 4. And so we can write HC in terms of the product of the coherence length and the London length, and the terms that are left over, well, there's a phi naught over 2 pi mu naught, and I think there's a 1 over square root of 2 remaining from here. Okay? So what does this mean? What this means is the following. It means that if you have a box, roughly a length scale psi on one side and length scale lambda on the other side, when you apply a magnetic field such that there is one flux quantum, roughly one flux quantum, maybe this is a bad idea, so I'll just write this, one flux quantum, one phi naught, through that box, that is roughly what the magnetic field associated with the critical field. So you destroy superconductivity when the magnetic field penetrating through a box, which is coherence length on one side and London length on the other side, when that box contains one quantum of flux, that's when you hit the critical field and you destroy the superconductivity. Okay, so that's a fairly accurate result. It comes out of Ginzburg-Landau theory and London theory. Okay, now let's recall a little bit of information about the distinction between type 1 and type 2 superconductors. So type 1 versus type 2 superconductors. I guess other fields aren't too much more creative in their nomenclature. That you have people who are like type A personalities. The truth is that I only ever hear people talk about type A personalities. I don't even know if there's a type B personality, but maybe I should look that up at some point. So other fields aren't any more creative than we are. So anyway, with type 1 and type 2 superconductors, remember type 1 superconductor is the kind that you never get vortices. You destroy superconductivity before you ever get vortices. And in type 2, you have Meissner effect up to a certain field, HC2, and then HC1, and then at a higher field, you in between HC1 and HC2, you have vortices penetrating the superconductor and discrete vortices, and then at HC2, the higher critical field, you destroy superconductivity altogether. And deciding on whether you actually are type 1 or type 2 depends on the sort of the vortex line tension. So the tension on a vortex line is the energy per length of the vortex line of vortex. Let's call that epsilon equals energy per length of the vortex, and the critical field HC1, where vortices first penetrate through the superconductor, is epsilon over 2 phi naught. Okay, and if HC1 is less than the critical field that destroys the superconductivity altogether, then you get type 2 superconductor. And if the HC1 is higher than the field that destroys the superconductivity altogether, then you never have a chance to get vortices going through the sample, because you've already destroyed the superconductivity before the the vortices can exist. So this, intuitively, this makes sense. There is some energy per unit length of the vortex. If that energy is extremely high, then you just destroy the superconductivity before you can force a vortex through the system. Okay. Now, the thing that we still need to figure out is how big is this epsilon? How big is epsilon, or energy per unit length? And we can actually use Ginzburg-Landau theory to calculate this. So roughly, what we do in a vortex, a vortex kills superconductivity in a region which is the size of the vortex core, a region, let's call it pi psi squared. So psi is the radius of the vortex core, and so this will give you the area of the vortex core. Okay, so if you, oops, no, I don't want that. So here I have a two-dimensional, here's a three-dimensional sample. I'm applying magnetic field here. There's sort of a cylinder here around the vortex whose radius is a coherence length, and the superconductivity is destroyed inside that cylinder. Okay, good. Remember also that the energy per unit volume that I need to destroy, the energy or the condensation energy, well, let's write this out, condensation energy, or in other words, the energy that I lose for destroying the superconductivity is mu naught hc squared over 2 per unit volume. So epsilon, the energy per unit length of a vortex, is mu naught hc squared over 2 times pi psi squared, and the pi and the 2 I'm not going to get right anyway, so let's just call it mu naught hc squared times psi squared. Okay, squared like this. Okay, now that tells us, since I now know the energy per unit length, the tension, then I have hc1, the field at which, the so-called lower critical field at which vortices first penetrate through the sample, which is epsilon over 2 phi naught. This is then mu naught hc squared psi squared over phi naught. And then here I am going to use this identity. And I'm going to drop the 2 pi's in the square root of 2. So I'll just, well, let me copy it again. Here, I'm going to use this identity, which we just derived. Okay, sorry, paste this identity. I'm going to drop the square roots of 2 and the 2 pi, because we're not going to get those right anyway. And I'm going to substitute that in for hc, and I will get, well, it's hc squared, so the psi squared here is going to get canceled by the psi squared here from hc squared. I'm going to be left with a lambda squared downstairs, so I get 1 over lambda squared. Maybe I'll call this approximately equal because I'm dropping constants. And then we have the flux quantum upstairs. One factor of the flux quantum is left upstairs. We had 2 factors upstairs from here, and then minus 1 factor divided by mu naught. Okay, so what does this mean? What this means is if I have a box and filled with magnetic field, and there's roughly 1 flux quantum in this box, 1 phi naught. If this box is lambda on both sides, 1 penetration length on both sides, this magnetic field is hc1. Okay, so you hit hc1, the field at which vortices first penetrate through a superconductor when you have a magnetic field in a box of size lambda by lambda, which is one flux quantum. Good. So type 2, just looking at this equation here, type 2 superconductor, type 2 superconductor is Hc1 is less than Hc, and that occurs when? Well, this is when, just comparing this equation, Hc, to this equation here for Hc1, we see that this condition is basically, again, I'm dropping constants of order unity. This condition is lambda over psi is greater than 1. Okay, so let's see why that is. So if lambda, okay, so if I take the ratio of Hc to Hc here to Hc1 here, I'll drop it, so the phi naughts will cancel, the mu naughts will cancel. I throw away the 2 pi and the square root of 2, which I'm not interested in. And what's left? Well, 1 lambda cancels, and I'm left with a lambda over psi. Okay, so this is the condition for type 2 superconductor. Oops, that's still not working the way it's supposed to. Also, it's not working the way it's supposed to. It tends to, okay, that's not really square, but it will work. Okay, so we've derived from Ginzburg-Landau theory that when the London penetration depth is longer than the coherence length, then you have a type 2 superconductor. So typically what people do is they define a dimensionless quantity, called kappa, which is lambda of t over psi of t. And this quantity, remember that both of these quantities, when you're close to Tc, they both diverge the same way. They both diverge as the inverse square root of T minus Tc. So this thing is temperature independent in depth of T, close to Tc. And this quantity, in fact, we can write this out in terms of the Ginzburg-Landau parameters. It's actually 2 alpha 4 over mu naught, and then there's an m star over an h bar e star. Notice it does not have a factor of alpha 2 in it, because alpha 2 is temperature dependent. So all of this is temperature independent. And this ratio is known as the Ginzburg-Landau parameter. The Ginzburg-Landau parameter. I mean, sometimes people, okay, nomenclatural problem. Sometimes people say alpha 2 and alpha 4 are Ginzburg-Landau parameters. But if someone talks about the Ginzburg-Landau parameter, they're talking about this dimensionless ratio. And a more careful calculation, finds that we weren't too far off, throwing away factors of 2 pi and square root of 2 and things, that the real condition for type 2 superconductor condition is that kappa should be greater than 1 over square root of 2. So we were very, very close, throwing away lots of parameters and doing things very roughly. And we understand more or less how this works. Okay. One more thing that I guess we should be a little bit careful about. There's one piece of energetics that we sort of left off, and that is we used the following statement for the energy of a vortex per unit length. We used that the energy of vortex per unit length is mu naught hc squared psi squared. So psi squared was the area of the vortex, and this was the condensation energy per unit volume. But for an isolated vortex, there's actually an additional log correction. Actually, we left off some physics. Log correction for a single vortex, and it should actually be mu naught hc squared. I'm drawing more and more sloppily as I go along. Mr. Fraction is probably rolling over in his grave and being very upset with me, that there's actually a log, an additional log factor, log of the ratio of the Ginzburg-Landau parameter, log of kappa is left over. And to understand the physics of that log, I mean, we always, physicists, we always throw away log factors as not being very interesting. So let's but let's try to understand. I mean, sometimes logs, calculationally, they're not interesting because it's very hard to get a log that's bigger than 3 or 4. That you need something that's absolutely enormous before a log becomes a number like 10 or 20. So typically we're happy to throw away logs, but often there's interesting physics contained in knowing that the log is there. So let's try to understand where this log comes from, because it's kind of interesting. So around the vortex core, the superconductivity. Remember what's quantized in the vortex is the fluxoid, not the flux. And around the vortex core, you have flux, and then supercurrents start screening the flux as you go further and further out. So the order parameter. So if we're going to assume psi is less than lambda, and which is our condition for having vortices in the first place. And so let me draw. I tried to draw a picture like this in one of the previous lectures, and I don't think it came out very well, so let's see if I can do it better this time. So this is radius on this axis from the center of the vortex, and this curve here is going to be the superfluid order parameter. So the superfluid order parameter heals, okay, and then it saturates to the bulk superfluid density, the square of the superfluid. So this is the square of the superfluid density is what I just drew, and it saturates to the bulk superfluid density, and it heals over a distance scale, which is the coherence length. Okay. On the other hand, the magnetic field of the vortex heals over a different length scale, which is the London penetration depth. So if I plot the magnetic field as a function of radius, it's flat, 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 and then it heals over, or it gets screened over a much longer length. This can be much longer than psi, which is the London length, so the magnetic field goes as e to the minus r over lambda or something like that. Okay. Now, when we calculated the energy of the vortex core, we just said, well, we're destroying the superconductivity inside the vortex core here. But there's also an energy cost to having screening currents way out here. Okay, and it's easy to figure out what those, roughly what those screening currents should cost us. That if we had an unscreened vortex, the current in the theta direction would go as 1 over r. Okay, this is how, so that the curl of J would be 0. You require a current decaying as 1 over r if you want the curl of J to be 0. This is a neutral fluid, superfluid. I mean, curl of V. Call it the curl of V equals 0. It's what a neutral superfluid does. How its velocity gets screened. But that current flow actually costs you some energy. It has kinetic energy. So if the kinetic energy density is 1/2 mv squared, or density times v squared, density v squared, then if I want to calculate the energy of a screened vortex like this, I might want to estimate it by calculating the energy of an unscreened vortex out to a distance lambda. So I might calculate, this is sort of just a rough calculation, that the additional energy density that I missed, it is integral out to a radius lambda, d2r of 1/2 density times velocity squared, which is then integral, rdr, 0, integral from 0 to lambda r dr, and then the velocity goes as 1 over r, so this is 1 over r squared. So this integral then gives me a log of lambda left over, and then it gets normalized by psi. Okay, so this is where this additional logarithmic energy comes from that we dropped, we ignored. Okay. So that's an interesting piece of physics associated with the energy of a vortex. Okay, so this is pretty much everything I wanted to say about Ginzburg-Landau theory, and we're up to the point where we can stop talking about bosonic fluids and superconductors and start talking about fermions. But before doing so, I wanted to briefly go through the exam question that I promised you I would go through in this example. But I'll do that in the next lecture. The next lecture is going to be extremely short because I don't think it's going to take us very long to go through that lecture. But it's probably useful to have that in a lecture by itself, so it's easy to find. Okay, so I'll see you then.